Let's talk about something huge. I mean, truly massive. The global shipping industry. It's the engine of our entire global economy, moving something like 80% of everything we buy. But it has a pretty serious environmental problem, and the race is on to find a cleaner way to power it all. Okay, let's dive into this.
Look at that number, 1,000 million tons. That is how much CO2 the shipping industry adds to the atmosphere every single year. To put that in perspective, if international shipping was its own country, it would be the sixth biggest polluter on the entire planet. The scale is just staggering, and it's why finding a fix is so incredibly urgent. So, in this high-stakes hunt for a solution, one name keeps popping up as a serious frontrunner, especially as a way to start making a difference right now, and that name is methanol. It's being seen as this really practical first step on a very, very long journey.
So why all the buzz about methanol? I mean, what makes it so special compared to the other options? Well, it really just comes down to practicality. You look at something like hydrogen, you have to store that stuff at insanely cold cryogenic temperatures. Then you have ammonia, which is super toxic and comes with huge safety risks. But methanol, it's a liquid at room temperature. That makes it way, way easier to handle and store, using the kind of equipment people are already used to.
So, methanol is looking like a great choice, right? The industry thought so too, and they started building these new ships designed to run on it. But the moment these new engines actually hit the water, engineers ran smack into a bizarre, totally unexpected chemical puzzle. To get to the bottom of it, researchers did something really smart. They set up a real-world test, taking a brand new methanol-powered ship and comparing it directly to its identical sister ship, which was running on good old conventional fuel. Same engines, same lubricant, the only real difference was the fuel. And boom, right away they found the first big clue. This chart here shows the lubricant's protective power, what's called its total base number, or TBN. On the regular ship, you can see it's nice and stable, exactly what you'd expect. But on the methanol ship, the TBN was dropping. And not just a little bit, it was dropping significantly and randomly. Something was clearly attacking the engine's first line of defense. But here's where it got even weirder. They checked all the other usual suspects, the oil's thickness, its viscosity. Nope, no real difference. Signs of iron parts wearing down, nothing that stood out. They did see a tiny hint of extra wear on chromium parts in the methanol engine, but it wasn't a smoking gun. The only major distress signal was that crazy, unpredictable TBN drop.
So this became the million-dollar question, literally, considering the cost of these engines. If the lubricant can't do its job, the whole engine is at risk. But none of the standard tests were pointing to an answer. So why on earth was the oil failing?
And this is where the investigation took a really fascinating turn. The researchers started to wonder, wait a minute, what if the problem isn't just what's happening inside the engine? What if the problem is with how we're measuring it? What if the tool everyone was using was actually blind to the real danger? Okay, so let's quickly talk about what TBN really is. When you burn fuel, any fuel, it creates corrosive acids. The TBN is basically a measure of the oil's personal army of acid-fighting bodyguards. These are alkaline additives put in the oil specifically to neutralize those acids. So a high TBN means a strong defense. A falling TBN means your defenses are being used up. Now, there's another crucial piece of the puzzle, something called the tribofilm. Think of this as a microscopic self-healing shield. Special additives in the oil react with the metal surfaces inside the engine, creating this super thin protective layer. This shield is literally the last line of defense, preventing catastrophic metal-on-metal grinding. And here it is, the big twist. When the researchers mimicked the engine conditions in the lab, they found something shocking. The standard TBN test, it's completely blind to the new kind of acid being created by burning methanol. The test was never designed to see it. So that TBN drop they saw on the ship, it wasn't because the lubricant was fighting acid. It was just degrading from heat and other things. The test was completely missing the real fight. So, if the main test was blind, what was this invisible enemy that was actually attacking the engine? Well, this is where a separate study from another team of researchers comes in and provides that big aha moment. They found the smoking gun.
And they gave our villain a name, formic acid. See, unlike the strong sulfuric acid you get from old-school fuels, the incomplete combustion of methanol creates this weaker organic acid. And as they were about to find out, this new culprit attacks the engine in a totally different, much sneakier way.
The evidence they found was just damning. In their lab tests, they took fresh engine oil and dosed it with formic acid. And the result? A 10% jump in friction. That means the engine has to work harder, generating more stress, more heat, all because this acid is in the system.
But here is the number that really tells the whole story. 77%. That is how much more the engine components wore down when formic acid was present in the oil. It's a staggering number that shows just how destructive this invisible enemy really is.
So this is how it does the damage. It's incredibly clever, actually. The formic acid doesn't attack the engine's metal parts directly. No, it goes after the lubricant's special additives, the very things that are supposed to create that self-healing tribofilm shield. It stops the shield from ever even forming. So without that protection, the metal surfaces are left completely exposed.
Okay, so mystery solved. The culprit is formic acid. Its weapon of choice is preventing that tribofilm shield from ever being built. And now that engineers finally knew exactly what they were up against, they could get to work designing a smart solution. And what they came up with is a classic strategy, a two-pronged attack. First, you have to build a much better defense to protect the engine. And second, you need to go on the offense and tackle the acid at its source.
So first up, better defense. That means, for starters, formulating brand new lubricants specifically designed to stand up to formic acid. But it also means you have to change how you keep score out in the field. You can't just rely on that misleading TBN test anymore. Now, engineers have to track both TBN to watch for heat damage and something called TAN, the total acid number, which actually measures the buildup of formic acid. Together, they give you the true story.
The second part of the plan is to go on offense. I mean, why just defend against the acid when you can stop creating so much of it in the first place? If formic acid comes from incomplete combustion, well, then the solution is to make the combustion better. And researchers are already finding new fuel additives that help methanol burn cleaner and more completely. One particular, just called Candidate C, looks really promising for creating way less of that harmful acid to begin with.
And you know, this isn't just some fun science experiment. As the researchers themselves point out, this work is absolutely critical. It's what's needed to create the right lubricants and strategies to make methanol engines tough and reliable for the long haul. Solving this one puzzle is a direct, practical step towards making green shipping a real thing.
You know, when you take a step back, this whole story, this deep dive into one specific technical lubricants problem, it's really a perfect metaphor for the entire energy transition, isn't it? The road to a clean future isn't some simple switch we flip. It's paved with thousands of these hidden, complicated, interconnected puzzles that scientists and engineers have to solve one by one.
Which really just leaves us with one final thought. We figured this one out. We solved the mystery of the failing lubricant, but this was just one piece. What other invisible challenges in shipping, in energy, in everything? What else is lurking just beneath the surface that we still need to find and solve to build a truly sustainable world?